Okay. This is screencast number 5. We have to determine how the centripetal acceleration of the third car in the roller coaster is at the top of the track and compared to the centripetal acceleration of the third car, what was at the bottom of the track. So when you just compare the quantities, just like that. Question 2 is finding the normal force at the top of the loop and then at the bottom of the loop and comparing it the same way, but just with the normal force. The first thing I did was draw everything out. This is a roller coaster diagram. Before I split it up into 2 different diagrams, I wrote it obviously 240 frames per second. I just wrote this to kind of help me think of the forces. A force must act on it directed toward the center, and it must be accelerating towards the center. So what I did was drew out the roller coaster. I was just paying attention to the third car, and I made sure that I measured the beginning of the third car and the end of the third car so that I am able to get the velocity later, so that I'm able to measure the time from here to here. So I measured that. I have my radius of this big circle over here, which this is going to help me solve for my bottom. And then I have this circle right here, which this is going to help me solve for my top. Yep. And that's my free body diagram. Now I split up the free body diagrams so that I'm able to focus on each part separately. This is the top, and I drew out each one of the forces, and where the forces are facing. So at the top, centripetal acceleration is heading towards the center, just like as my little statement said. Weight's always going down. And now normal force is also acting towards the center with the centripetal acceleration as well. At the bottom of the roller coaster, we have weight down, we have normal force up as usual. Now this normal force is a little bit larger, and then we have centripetal acceleration also going again towards the center of the circle. I wrote my equations there, so we are going to have to use Newton's second law, and centripetal acceleration equals velocity squared over r. Now, looking at all the facts that we have, I listed all the knowns and unknowns. So we know the top time. I measured the top time between the car, and I measured the bottom time between the car. I don't necessarily need both, but I did that. We have the radiuses. Now, in order for us to get anywhere, we need velocity. We need the centripetal acceleration top and bottom, and the normal force in top and bottom. But in order for us to get anywhere, because for the normal force we're going to need centripetal acceleration, so therefore we need to get velocity in order to get to this part first. That's my equations of how I get to my time, converting from my frames to seconds for my car. We have velocity. Velocity equals displacement over time. It's x, the change in displacement over the change in time. Once the car is right here, it is actually parallel to our scale. We're able to measure the x1 to x2 and find the displacement in between of the car. We got 2 meters for the distance of the third car is the only thing we were measuring. So we were able to find them by doing 2 meters divided by our time. We were able to find our average velocity, which is 15.04 meters per second, which is great. Now we can plug that in. The first step I did for both the top and the bottom was solve for centripetal acceleration. Now that we have our velocity, we just square it and put it over the radius. For the bottom loop, it's this big loop here. Also this one. So we're going to use this radius. So it's times 16, which is 14.14 meters per second. And then here, we're going to use the top, which is 4.4 is what our radius is. And we got 51.41 meters per second squared. Surprisingly, I figured that the bigger circle was going to have bigger centripetal acceleration. But we're just measuring the top and the bottom. So, anyways, this was a little bit surprising to me, but this is what I got. So the ratio when I put it over top and bottom, I got approximately 3.64 to 1 ratio. So the top is bigger than the bottom, approximately 3.6 times. Now we're able to find our normal force. So in order to find a normal force, we could just use Newton's second law. We know that the sum of forces equals mass times acceleration. Now at first I didn't put this on there, I just had it like this. But we know at this time, because it's circular, we're dealing with centripetal acceleration. So I could go ahead and put the C. Same thing with on the other side. Now I drew out my forces so that I'm able to we're still dealing here with the bottom, so that we have a force going to the center, positive, and then have weight going down, negative. So the sum of force is going to be Fn minus mg, or n minus w, but I did Fn minus mg equals, you could have m v squared over r, but since we already solved for v squared over r, I just plugged it in, which is centripetal acceleration. Therefore, we want to solve for n, for force, normal force. So just bring everything to the other side. We're just gonna add 2mg. We could take out the m's and solve for it, which is just gonna be 14 plus 9.81. But 1 newtons is equal 1 kilogram per meters per second squared. Technically, we do need the mass in kilograms in order for us to get a newton. We could also get a ratio just by taking out the m, since we don't know the mass. I did also try finding the mass on the internet, but I got many different numbers, and not for the Corkscrew roller coaster. So that was a little bit challenging, but I think you're still able to make the ratio and the overall concept. Over here, the same thing. The sum of forces equals MA, and then I wrote the forces down over here. So this time they're both going towards the center, mg and normal force. So we did Fn plus mg this time equals, again, you could have v squared over r. I just plugged it in since we already had solved that. So Fn equals centripetal acceleration minus mg, just putting it on the other side. And we don't know the mass, we don't know the kilograms. I did try looking that up, but there was not an exact mass for it. Although you could pretty much tell still that the Fn of the top loop is going to be approximately 2 times bigger than the bottom of the loop. But again, 1 newton is 1 kilogram times meters per second squared. Here we have only meters per second squared, which we know our g is 9.81 meters per second squared. So we don't know our mass, which we kind of need, but you could still tell the main concept of what's going on.